Vector addition, scalar multiplication has a set of properties, important properties. These are properties that we sort of think of as being valid whether the vector has two components or n components, right? This is something that's specific to these geometrical vectors, these vectors in n space. So the properties are as follows. Let's say you have three vectors in n space, u, v, w, and you're going to pick two scalars, c and c prime. When I don't specify what u, v, w, c, and c prime are, what it means is that you're not allowed to pick specific values for those. It's got to be true no matter what the value is. You can illustrate these properties by picking specific values if you want, but that is not a proof, right? That's just an illustration. We're saying that these things are valid no matter what the choice of u, v, w, c, and c prime are. So if you're asked to show that a property is true, it is not sufficient to come up with an example and to show that for that example the property applies or the property holds. You need to show it in general. So there's these 8 properties. The first one is that adding the 0 vector to any vector leaves the vector unchanged. It's good. So 0 behaves like a 0. You add 0, you should get nothing new. If you reverse a vector, if you add u or a vector to its negative, then you get the 0 vector. Third property is that vector sums are associative. If you have to add u, v, and w together, it doesn't matter whether you first combine u and v and then afterwards add w, or if you first combine v and w and afterwards add u. You'll get the same result, which is part of the reason why we don't put parentheses here. There's no need to sort of group those together. Vector addition is associative, so you don't need parentheses. Well, you'll say, well, that's always the case. Why do I bother with this property? Sure, it's the case for vectors, and eventually we're going to see vector spaces, but we'll see that there are types of additions that don't satisfy these properties. At least we won't see that, but it's conceivable that you can come up with operations that don't satisfy this property or other properties. When a property satisfies, or when an operation satisfies this property, we have the tendency to call it an addition, a sum. But in advanced courses, you will see that you can define operations that are sums because they satisfy this property, but that don't really behave like a sum would. You're not even adding numbers together, you're adding other things together. And when the property doesn't, or when the operation doesn't satisfy these properties, but satisfies other properties, we tend to call them products or multiplications. That's neither here nor there, it's just something for advanced courses. Another thing that's a property of vector sums, vector addition, is that they are commutative. U plus v, same thing as v plus u. You can reverse the order of addition without changing the outcome. That's a property that geometrical vectors have. It's a property that complex numbers have, real numbers have. It's a property that we like in general. But it's not guaranteed that an operation satisfies it. You can distribute a scalar on a sum as you would expect, as you do for numbers, right? So c of u plus v, that's cu plus cv, which in general is not the same as cu plus v, right? You have to put the c in front of both the u and the v. You can also distribute a vector over a sum of scalars. This makes sense because this thing is a scalar. C is a number and c prime is a number. C plus c prime is also a number. But if we're talking about vectors here, then we'd have a vector times a vector, and that's not always defined. So you would get this one and then this one. The scalars are associative as well, right? C prime U. You can first compute C and C prime, the product, and multiply by U, or you can first compute C prime U, multiply by C. And because scalars come from the space R, right? These are numbers, and because R is commutative, you could also write this as C prime CU. Now, when we write prime here, you got to be careful. We're not talking about the prime of calculus, which is a derivative. You're not differentiating a constant to get 0 here. C prime just means some other constant, different potentially, but not necessarily from the initial constant C. The last property we have is that there's a special real number 1. That special number, when you do scalar multiplication of any vector by it, well, you get nothing's changed. You're still at U. These are the properties that will be key to generalizing vectors to vector spaces, not just Rn, not just n space. We'll talk about different types of vector spaces, things that behave like vectors without being arrows. And these are the properties that we will want them to follow.